Hey everyone, this is the final part of chapter 3, storage and retrieval. And in this video, we'll talk about the concept of data warehousing and column oriented storage in databases. Now, before jumping into data warehousing, let's see what are OLTP and OLAP databases. Now, the OLTP databases are the ones which are designed to handle and process high volumes of real time transaction. They are optimized for transactional operations such as inserting, updating, and deleting of data. OLTP databases are commonly used in operational systems where data is constantly changing. And the examples are e-commerce websites, banking systems, airline reservation systems, and also point of sale systems. On the other hand, OLAP databases, they are designed for data analytics, complex analytical and reporting tasks. So they allow the users to perform aggregations and multi-dimensional analysis on large data sets. And these are the main differences between OLTP and OLAP databases. So in case of OLTP, there are smaller number of records which are fetched per query. On the other hand, in case of OLAP, a query usually aggregates over a large number of records in the database. Also, the end users of OLTP DBs, they are usually end users and customers who can access the data via web application. Whereas for OLAP DBs, the analysts, they have to run the queries, the analytical queries for decision making. Also, OLTP databases, it represents the data in the current point of time. Whereas in case of OLAP, they have mostly historical or archival data. And that's why also OLAP databases, they are like terabytes or petabytes in size. While in case of OLTP, they are usually GB, they are usually in the order of GBs or terabytes in size. Now these OLAP databases, it leads to the concept of data warehousing. So usually an enterprise, they have dozens of different transaction processing systems. So for example, they have systems powering the customer facing website. They have systems for, they have checkout systems in physical stores, for also for tracking inventory in the warehouses, for planning routes for vehicles and so on and so on. And all these OLTP systems, they're usually expected to be highly available and to process all the transactions with very low latency, since they are very critical to the operation of the business. Now the database admins, they usually have to guard their OLTP databases. They are very reluctant to let business analysts run their ad hoc analytical queries on the OLTP database, because those queries, they are very expensive, and also they tend to scan large parts of the data set, so they can very much harm the performance of the concurrently executing transactions. So that's why data warehouse, it is a separate database that the analyst can query without affecting the OLTP operations. So the data warehouse, it contains a read-only copy of the data in all the various read-only copy of the data for all the various OLTP systems in the company. So data is extracted from the OLTP databases using either a periodic data dump or a continuous stream of updates, and it's transformed into an analysis friendly schema. It is cleaned up and then it's loaded into the data warehouse. So this process of getting the data into the warehouse is known as extract, transform, and load. Now Teradata, Metas, Presto, Apache Hive, Impala, these are all the examples of data warehousing systems. Now, before looking at column-oriented storage DBs, and let's see how the row-oriented storage works and why do we even need the column-oriented storage. So the column-oriented storage DBs, they are needed for our use case of data warehousing, and we'll get to that in a bit. So in most OLTP databases, the storage is laid out in a row-oriented fashion. And what that means is that all the values from one row of a table, they are stored next to each other. So for this table that we have on the left, the product table, in case of a row oriented storage, all the values from a row, for example, for this row 31 banana, fresh max and fruit, they're stored in one file. And the similar case for all the other rows. So all the value in the second row will also be stored in a different file, and for the third row it will be stored in a different file. Now let's say we have a sales table where all the sales related data is stored, and it can have columns like product name, the store name, the quantity, discount, price, and all the various other fields. So also let's assume that this big sales table, it has 100 columns in total. Now let's say if we have to, if we have an SQL query where we want to get the values from only these 4 columns from this table. Now I've written the column names like col1, col2, col50, but it can be the names of any 4 or 5 column names from the sales table. So in order to process a query like this, a row oriented storage engine, what it will have to do is it will need to load all of these rows, and each of these rows, they have 100 attributes. So this row oriented storage engine, it will load all of these rows from the disk into memory. It will parse them, and then it will filter out those that don't meet the required condition. So for example, in this case, we only want this 5 rows from the table. So first it will load all the rows which will have 100 columns. Now it will filter out only those 5 rows, and then it will return the result to the user. Now this process of parsing all the columns and then filtering, it can take a very long time. So, and that's where the column oriented storage, it comes into play. Now the idea behind a column oriented storage is really simple, that you don't store all the values from one row together, but you store all the values from each column together instead. So if each column is stored in a separate file, then a query only needs to read and parse only those specific columns which are being called for in that query, and that can save a lot of work. So for example, for this table that we have on the left, the product table, in case of a column storage, all the values in this column, for example ID, they are stored together. So for this product table, we'll have overall 4 files, and each file will have contain values from each of the columns. So this is why the column oriented storage DBs are very useful. Now another property of column oriented storage is that it often lends itself very well to the compression of data. Now if we take a look at the sequence of values for each column in this table, they look like quite repetitive, which is a good sign for compression. For example, in the product ID table here, the value 69 is repeated 3 times, and also 31 is also repeated 2 times. And this can be observed the same for the other columns also. For example, in case of store ID also, we have a lot of repeated values here. Now using this property of columns having repeated values, we can actually use this for compression. So one compression technique that is particularly effective in case of data warehouses is bitmap encoding. So for the column ID, for the column product ID in the sales table from the last slide, we have these values for each row. So the product ID, it's taking the first 3 values are 69, then we have 74, and then we have 231s. Now we can see that there are only 3 unique values in this column. So for the value 69, so this is how the bitmap encoding will work. So for the value 69, we'll put a 1 for the column where the value is 69, and then we can put 0 otherwise. So similarly for the value for the product ID 64, we put a 1 for the columns where the value is actually 74. So in this case, it's only this 4th entry here. Now, so this is how we can use bitmap encoding to compress these column values. Now we have another technique, it's called run length encoding, which can further compress these bitmaps. So run length encoding is nothing but it's just a way to compress the binary numbers that we got here using number of times that we have these consecutive ones and zeros. So 033 here in this case, in case of run length encoding, for the product ID 69, what it means that we have 0 number of zeros, and then we have 3 ones, and then again we have 3 zeros here. So in case of product ID 74, we first have 3 zeros, that's why the number 3 here, and then we have 1 1, that's why the number 1 here, and then we have 2 zeros. So that's why we have the number 2 here. So this is how we can compress each column into just few small set of values using bitmap encoding, and then further applying run length encoding into that. Now bitmap indexes such as these are very well suited for the kind of queries that are common in a data warehouse. So for example, for this query, let's say it's trying to find a product ID, and it has to find only those product IDs which has these matching values. So for this query to find the results for either of these columns, the system, it will load the 3 bitmaps for the product IDs 30, 68 and 69, and then it just has to calculate the bitwise OR for the 3 bitmaps. And that bitwise OR operation, that can be done very efficiently. Similarly, let's say if we have a AND clause in this where condition that we have, so the system can calculate bitwise and for the bitmaps for these corresponding product IDs. So this is how, using column compression, we can very easily column oriented storage, it can very easily calculate the or parse the values for queries like this. So all these optimizations, it makes sense in data warehouses because most of the load, it consists of large read-only queries which are run by the analyst. However, they have the downside of making the writes in the DBs more difficult. So to overcome this problem, we have already seen a very good solution, and that is LSM trees. So all the writes, they first will go into an in-memory store in this case, where they are added to a sorted structure, and then they are prepared for writing to disk. So it doesn't matter whether the in-memory store is row-oriented or column-oriented. When, let's say, enough writes have been accumulated, then they are merged with the column files on disk, and then it's written to the new files in bulk. So this is how a write to a column-oriented storage DB will work. So this is the end of chapter 3, storage and retrieval. Next we'll look into chapter 4, which is data encoding and evolution.